Hi, today's topic is recursion. Before covering that, I'm going to review last class topic, strong induction. Yeah, we have seen this inductive proof in 5 easy steps, and we can prove this inequality using that. So there is another example, and this is strong induction. What's different from induction and strong induction? Induction only use um, previous step, one step before the current step. So when you prove P of k plus 1, induction only use P of k, but strong induction used all the k's before current status. If you want to prove k plus 1, you need to assume P of k, P of k minus 1, k minus 2, the P of 0, they are all true. Then you can prove P of k plus 1, and then you can prove P of n for all integer n. So this is original induction, and this is strong induction. And so here, the additional assumption, yeah, P of j is true for every integer j from b to k. So then you can prove P of k plus 1 using that. Then finally, you will conclude your claim is true or not. So this is one example using the strong induction. So every integer greater than equal to 2 is a product of prime. So the base case, so we know 2 is a prime, so that's why this is a product of prime. That's true. So we assume P of j is true for every integer j between 2 and k. So we need to show P of k plus 1. K plus 1 is a product of prime. So we can think about two cases. If that is a prime, k plus 1 is a product of prime, true. If that is composite, then we can assume that will be a product of two number, and we already know about this will be product of prime because there is the sequence before this. We don't know. That will be k minus 1 and k minus 2. There is a number before this k plus 1 that is the product of prime. So A is one of them, B is one of them. They are all product of prime. So if we multiply them together, product of prime and product of prime, so this is product of prime A, product of prime B. So k plus 1 is A multiplied B, that is definitely a product of primes. So P of n is true for all n is greater than or equal to 2 by strong induction. Yeah. Strong induction is particularly useful when we need to analyze method that on input k make a recursive call for an input different from k minus 1. So previously, we don't know about a and b. That is k minus 1, k minus 2, k minus 3. It doesn't matter. Anyway, that is one of the previous element. Then we can use that to prove next step. Okay, and there is another example like binary search that is recursive function. So when you need to prove this kind of thing, you may need recursive definition to prove it. So here is example. So we have factorial and exponentiation. So how to compare? So factorial is kind of recursive function. So n factorial is n multiply n minus 1 factorial. So n minus 1 factorial is n minus 1 multiply n minus 2 factorial. Because of that, we can use that in the induction step. So we know the previous step is factorial, and we can multiply current step, current number to that. That we can make the current factorial. So here is the step k plus 1 factorial is equal to k plus 1 multiply k factorial. Right, we know that. And if we multiply this part to the p of k right side, k to the k's, it will be like this, and this will be smaller than this, and this will be like this if you apply this simplification. So this one is same to p of k, and this one is p of k, so that means p of k is true. P of k plus 1 is true. So we can prove this using induction and definition of factorial. Okay, next step is recursion.